Okay, so for this question, we have analyzed the situation and we see that the gas is expanding, so it means that it's doing the work to like lift off the mass. So the work done by the gas is a positive quantity. And if we use this approach of the first thermodynamic law, we cannot solve it yet because we don't know the amount of heat yet. It is not given yet. So is there any other approach we can use? Let's leave it for now. Maybe we may need to use it later, but maybe not. Okay, so what is the other approach that we can use? There's another hint here. It's a constant pressure. So actually this is a process with a constant pressure, right? So when we have the pressure as a constant, that is a isobaric process, right? Yeah. And do you remember any special thing about the isobaric process? Is there any formula we can use? There is, right? So what is that one? That is the V initial over T initial equals to V final over T initial, T final, right? So actually, do we know VI? We do. Do we know VF? Yes, we know. Do we have TI? Yes. So can we find TF? Yes, right? So it's pretty simple. It's just another approach. So T final will equals to VF over T, over VI times with TI, right? Just plug in the values, then we can find it. Okay, the VF here, they said it will be the AII. So AII is this much, right? 1.3 times 10 to the minus 2. 1.3 times 10 to the minus 2 meter cube over, what is the VB? VB is at 1.2 times 10 to the minus 2 meter cube times with the initial temperature, which is 300 Kelvin, right? 300 Kelvin. Yeah, we need to write this way so that we can remember that there are like three significant figures. So this one have two significant figures, this one have two significant figures, this one have three significant figures. So if we add them together, we should have the result of the two significant figure. Okay, so let's just plug in the values and then find it. It will be around 3. Oh yeah, here this is about, this is also like about, and if you check the math scheme, they actually try to have more significant figure. They end up with this one, more exactly to be 1.348, okay, and this one to be more accurate with 1.160. Okay, they have 4 significant figure for the values. So the T will end up around, I will use the value with more significant figure, around 3.48, but I will just yeah, I will keep it with 3 significant figure. No, yeah, with 3 significant, because with this one we have that 3 significant figure, so I will keep it as like 3 significant figure times 10 to the 2 Kelvin, so it's about 348 Kelvin. Okay, actually if you use the calculator, you will see there's another 6 behind. So if I round it up to be 3 centimeter, it should be 3.49 times 10 to the 2 Kelvin. Okay, so let's have it this way. Okay, then C, for the change in B, show that the thermal energy supply. Oh, so you see that actually we still need to use what we had before, but that's for the next question. Okay, so basically the Q in this case, and we should use the first. This one is good enough, right? The firm. So let's just keep this one. We got the change in delta U, right, to be NR. This is the T final that we just found minus the T initial, and then plus with the work done by the gas as pressure doesn't change. Then this one should be the pressure times with the change in the volume. So we can also make it clear to be the volume final minus volume initial as well. Then just plug in the values. You can find it to be the change in this one. Oh, I'm missing the coefficient, 3/2 as well, sorry. And then this one will be 3/2 times with the n. What is that value? 0.5 mole times with the constant r, which is 8.31 for the units as in joule, mole to the -1 and Kelvin to the -1 to cancel out with the temperature. Here is actually, this is like 49 and this is like 300, so that's around 49 Kelvin, right? If you want to make it more accurate, you should use the values that have been rounded up yet, like 48.6, okay? But it should be okay if we use 49. Plus with the pressure stay constant here to be as 1.075 times 10 to the 5, because that will be the pressure in the B, right? That's the pressure in the B. And times with the change in the volume is later. That's the two values we have here from the previous finding. And you can double check it with the mass scheme. So these also like times 10 to the -2 in the meter cube. Okay. Oh, the pressure, I should be clear here. This is Pascal as well. Yeah, we need the unit for the pressure to be in Pascal so that it can cancel out with the volumes in meter cube here, and then what we left will be in joule. So just plug in the values, then you will find it's around 500 or 5 joule, right? Yes. And then last question, the student claims that the change in entropy is around this, so comment on this claim. So you can see that if we just use the formula itself, we will need to plug in the values of the T. So then would you ask yourself that what kind of temperature you should use, right? Should you use the 300 Kelvin or should you use the 348.6 Kelvin, right? And the answer is that we cannot use this one because the temperature is not a constant. So we cannot use this value. This value only apply when you have T stay constant, okay? So basically, this one, that the formula cannot be used. The formula cannot be used because the temperature is not a constant. Because the temperature is not a constant. It has been changed. Okay, so that's question number 3. Okay, please let me know if there's anything that unclear, and good luck in your upcoming exam. Thank you.